Hello everyone. We are going to finish chapter 2 by looking at chemical kinetics. You can find information on this in your textbook in pages 42 through 47. So there's two aspects that we'll look at when studying kinetics. First, we are going to study reaction rates, how the concentration of something changes over time. And we're also going to look at reaction mechanisms or pathways and how chemical reactions proceed. The latter we'll do less of. We'll mostly focus on rates and thinking about how reactions actually occur. Why is this important? Well, this is important because kinetics allows us to understand whether or not a system will reach equilibrium. That's very important for natural systems because we need to know whether the system is at equilibrium or not so that we can study it correctly. And so one variable that we will cover in kinetics is the half-life. So the half-life tells us that, say we have a certain concentration of something to start with. The half-life, one half-life I should say, tells us the time it takes for half of that to be gone, or the time it takes for half of the reaction to occur. And so we can relate that to the, say, mean residence time, which is related to equilibrium, right? That's kind of our average time in which we can get the system to turn over. We say, oh, it's at equilibrium based upon the mean residence time. So what we'll find is if the half-life is less than the residence time, so that means that the reaction is actually moving quicker than the residence time. We say that, well, the system most likely has reached equilibrium. So again, this is showing us that it's important to know the kinetics. It's important to take time in understanding the quickness of these reactions relative to the residence time. And then we can say that if the half-life is much greater than the residence time, that's saying that the reaction is taking longer than what we assume to be the residence time, then we need to actually use kinetics to describe the behavior of the system. And thermodynamics is not the best way because it's not at equilibrium. So this plot is in your textbook. It relates the reaction rate with the residence time. So just as I just was describing about the system and considering the half-life, we can do that with this figure as well. So here we have the residence time, different residence time for different types of systems like streams, lakes, and ocean. And then here we have half-lives or reaction times. And this is for different processes like adsorption, desorption, or crystallization, things like that. And we're on different time scales of seconds, hours, to years, those sorts of things. And so let's say if you were considering studying some streams, well, you could approach the system as an equilibrium if you're studying, say, adsorption, desorption, or, you know, solute-solute interactions, things like that. That would be okay in a stream, and you could use a thermodynamic model. But if you were considering mineral water equilibrium, well, the mineral and water will not be at equilibrium in, say, a stream because the half-life of that equilibrium is much longer. It's more on the terms of months or years, and streams you are essentially studied more in hours and at the most days. So I hope that kind of gives you a simple example of kind of how we need to think about whether kinetics is important or whether thermodynamics equilibrium is important. And so I showed you this plot in the last activity that we did, but remember, up to this point in studying thermodynamics and equilibrium, we've only been interested in the reactants and the products. So in equilibrium, it's the products over the reactants. In thermodynamics, it's the initial and final states, the reactants and products, the state in which they're in, and their energies. What we're going to cover now is this middle section, the pathway. How did they actually get there? There's a lot to it. It can be simple looking like what you see here, or it can have lots of bends and curves to it as well. So a lot of times it has a contour to it in terms of what path, even with just respect to energy, the reaction took. I also wanted to bring this plot back into discussion because, there's my cursor, because this region here, this is where we're at in terms of CO2 emissions and temperature change, where we are not, in terms of the carbon cycle or in terms of climate, in a state of equilibrium. We are in a state where we need to be studying the kinetics because things are changing over time, and that needs to be our approach to climate change, not studying it as an equilibrium problem, studying it as a kinetic problem. Someday, of course, when we reach this region here, we'll be long gone. But once we are in this region again, where things are no longer changing over time, then we can start treating it again as a equilibrium problem and think of it in terms of thermodynamics and residence times. And so I'm going to give you a quick review or introduction. Some of you have studied kinetics before, some of you haven't. It's not an issue if you haven't. You will learn what you need to during this lecture and during this course, and it will benefit you later on. We'll use kinetics later when we study radioactivity, and kinetics is also really important in things like atmospheric chemistry. And so let's take a generic reaction. Let's say A plus 2B goes to some products. Now, when we write these equations, like what you see in a lot of textbooks, a lot of times there's actually more to this reaction than just the overall reaction. Many times this reaction is made up into multiple reactions that are stepwise add up to the overall reaction here. So for example, like we say here, maybe this actually occurred in two steps, where the first step was A plus B went to, say, I, which I is abbreviated for an intermediate. This occurs a lot of times. You don't ever see the intermediate in your equation because it's created in one step and consumed in another. But this is very common in many chemical reactions. So the intermediate then, we'll say, goes on to react with B to produce the product. Well, we add these two equations. I cancels out on both sides. We get an A plus 2B's equals the products. So this is what you see in the textbook, but how we actually got here was actually a lot more complicated. So this is, again, is an example of a reaction mechanism. So we're primarily going to cover rates in this class. That's how we're going to use kinetics later on during the semester. So let's take our generic equation and let's talk about rates. And so the rate of reaction is defined as either the formation of the products or disappearance of the reactants. So you can frame the rate either way. If you frame the rate as products, well, it's going to be in terms of the appearance of the products. So products form over time. So I have d, the concentration of P over dt. So this is, I'm using, in this lecture, I'm using notation that is used in calculus. Rather than using the delta, I'm using a d. But the little d just means change in concentration. We have up here, change in P over the change in time. But we could also write an expression for the rate in terms of the concentration of A. I can say that the negative here, it means the disappearance of A over the change in time. So that is also a way to write the rate in terms of the variables. Or I could say the rate is equal to minus 1/2 the change in B over the change in time. Now, where did that half come from? Well, I have an equal sign here. And so if I'm going to relate the change in A, the disappearance of A, with the disappearance of B, for every A that disappears, two B's react with that to make the product. So that means that I need to relate that, and that actually B is disappearing twice as fast as A. So to make them equal, since B is disappearing twice as fast as A, I put a coefficient here of 1/2 to balance those two off. So we see it in this plot. If I plotted the concentration versus time for this reaction, I see the disappearance of A here. And if that's the disappearance of A, then B is going to be consumed twice as fast, right? So it's dipping down twice as fast. So there's my times 2. And then we're getting the formation of P right there. And what we also see is in this region here, all of this region up until about this point, this region, we're seeing the part of this reaction where kinetics is important. Kinetics is important because we're seeing changes in concentration. At any point on these curves, we could take the slope of these curves and we could calculate the rate of the reaction. But at a certain point, the reaction goes to completion. And that's where we are at this point. Once we reach this point here, as we go this way, we notice that the concentrations are no longer changing. We can see that the change in concentration over time is 0. And that is when we're at equilibrium. So at this point, we've reached the thermodynamic domain where we can treat the system at equilibrium. In this region over here, we treat it with kinetics. And so again, we can write the rate in terms of any of the products and reactants, and we can find that rate by measuring the slope along the progression of the reaction. So now that we understand rates a little bit better, and we understand when we're interested in kinetics, when we actually see the products and reactants changing, what we can do with that is we can actually model it with mathematics using the rate law. And so what this equation does, and that's what the rate law is, it's an equation. It relates the rate with the concentrations of the reactants. So once we have it written, we can model that curve that you saw on the previous slide with the equation. And in order to write a rate law, you just need a few pieces of information about the reaction. And so here, this is a rate law, and I've written it as the change in the product over change in time, and it's equal to a rate constant. You always have a rate constant in your rate law. This kind of bridges what we have over here in terms of concentrations, and it bridges it with what we have over here in the rate. And here I have my concentrations of A and B. This is for my generic reaction of A plus 2B goes to P. And I have these concentrations, and then I raise these concentrations to what we call the order. This is a very important aspect that we'll cover in this video, is the order of reaction. The order tells us the behavior of the reaction and how the reactants will disappear over time. So depending upon how they collide and react, sometimes it's one way, sometimes it's the other. It's all based upon the order. And each reactant has its own order. So again, the order of the reaction describes the behavior of the concentration of reactants over time. So in the next part of this video, we're going to look at 3 types of orders: the 0th, the 1st, and the 2nd order. So let's start with the 0th order. That's the simplest of the 3 orders. And this is where the rate is independent of concentration. So this is an example where the rate is constant. It stays the same no matter what the concentration is. The concentration could be low, it could be high, it doesn't matter. The rate is what it is. And so it's independent of the concentration. And what that is telling us in this scenario is that the rate's being controlled by something other than what's in the reaction. A lot of times this could be, say, a catalyst. The catalyst is actually dictating the rate. It has nothing to do with the reaction itself. in terms of the concentration of species, or maybe the reactants are reacting on a surface like a catalytic converter, and that surface is what controls the rate. Or maybe it's flow dynamics. Maybe it's just being able to deliver the reactants through flowing such that they react somewhere and make the product. Or another form of catalyst in biology is enzymes, and it's actually the rate of turnover in the enzyme that controls the actual rate. But again, whatever the case, zero order, it's not affected by the concentration of the reactants. So we can write a rate law for a zeroth order as the disappearance of A over time equals a constant. And as we go along in this video, we're going to start collecting equations for the behavior of these reactants in a given order. And so for zeroth order, we have a half-life equation now, and we have an equation here that relates concentration and time, given that we know the initial concentration. This A naught here is initial concentration. And then this A here, this concentration is the concentration after so much time. So we have the rate law, we have the half-life equation, and we have what we call the integrated rate law equation. So now let's do first order reactions. So in zeroth order, the rate did not change versus concentration. But here, if we plotted the rate versus concentration, we get a straight line. And what this is saying is that the rate increases as the concentration increases. If we plot concentration versus time, what we'll find is that this is actually an exponential decay reaction for first order. And the products will form logarithmically increase over time. And so an example of a first order is, say, the rate of reaction to form the products is all about A. It's all about how A goes to products. An example of this would be radioactive decay. And there's lots of examples where we have first order reactions. But radioactive decay is a very common one where, say you have some uranium-238 and it's just sitting there and it will decompose following first order kinetics, where it'll decompose into thorium-234 and an alpha particle. At higher concentrations, the rate is much faster than at low concentrations. That's what gives us this exponential decay. And with this curve, we have a hard time thinking in exponential functions. But if rather than plotting the concentration of A versus time, let's concentrate or let's plot the natural log of the concentration versus time. If we do that, we get a straight line where the slope is equal to negative k. And the y-intercept here is equal to the natural log of A naught being the initial concentration. So for first order, we have a rate law. Following our template, we're going to say that the disappearance of A, our reactant, is equal to K, concentration of A, its first order, so the exponent is a 1. So we don't need to put a 1 up there. We know it's a 1, but there is a 1 up there, and that exponent is saying that it's first order. So you should be able to recognize that this is indicative of a reaction that's obeying first order kinetics. From this plot here, we get two equations. We get the slope of the line. This is in mx plus b form, where the natural log of A equals negative kt plus natural log of A naught. So you're going to use this equation when you're dealing with first order reactions, and you can relate the concentration with time. If you know the initial concentration, you'll be able to figure out the concentration at some amount of time. And we also have the half-life equation here, where the half-life, how long it takes to get halfway, so this would be the first half-life, this would be the second half-life, and so on. If this was A naught up here, this would be half. This would be the first half-life. This would be the second half-life, and so on. It's equal to the natural log of 2 over k. The number for natural log of 2, if you put in your calculator, you get 0.693. And so you'll see both of these forms used often, and they're the same. So we're going to use this equation later on, and we'll use this equation later on. And again, they're only used for first order. We can do the same thing with second order. Second order reactions, if you plot the rate versus concentration, rather than getting a straight line, it's more of a parabolic function when you plot the rate versus the concentration. So that means at higher concentrations, the rate really goes up. And so an example of a second order is when, say, A collides with A to make a product. So what's happening here is the rate depends upon the concentration of A and the concentration of A. So it depends upon both of them. And so it's magnified in terms of how concentration affects the rate. And that's why it's really getting steep. That would be, or say this rate law here, where I write the disappearance of A over time is equal to a rate constant, concentration of A squared. It could also be written as equal to, say, K equals the concentration of A times the concentration of A. That would be another way to write it. We could also say from our generic equation, perhaps the rate is dictated by the concentration of A and B, that both of the collision between those two is what dictates the rate. Well, then we would write a rate law. It would still be second order because the rate is affected by the concentration of A to the first power, B to the first power. Well, you add these two powers, to get the overall. It's first order with respect to A, it's first order with respect to B. The overall order is second. Just like up here where this is with respect to first order of A times the first order of A, that gives us the overall order of second as well. But what it's trying to describe, again, in second order, that the concentration of both species and their reaction creates this second order reaction where the concentration of both of them affects the rate. And so an example that I thought of, at least in my research, that I think about is particle formation. So let's say you're in the Arcata Marsh, and that is where you have lots of particles, and those particles are always colliding. You know, the water's slightly moving, they're colliding, and slowly we're getting particle formation where smaller particles turn into bigger particles. And so the more particles you have, the more this aggregation coagulation process will occur. So if you have a lot of colloids, you'll form a lot of particles very quickly. But as the concentration of colloids goes down, the rate of aggregation goes down. And I will also say that this rate is twofold in that it depends upon how many colloids there are, plus how many colloids there are. It's twofold. It's a second order reaction. So if we plot the concentration of A versus time for a second order, we get a very steep curve. And if we plot 1 over A over time, we get a straight line. We like these types of plots because it's easy for us to get information out of them. So again, if we plot 1 over A versus time, we get a straight line where the slope is equal to K. And so we have our rate law here. It looks like I dropped a 2 here. This needed to have a 2. And so here's our rate law. And then here's 2 more equations for second order reactions. So here's my integrated rate law, where I can relate time and concentration. And here I can calculate the half-life for a second order reaction. So this slide kind of sums it all up. So I want you to be able to use these reactions, or I should say rate laws, and also equations to calculate certain aspects of a kinetic system. I also want you to be able to know the behavior of a first order, second order, or zeroth order equation or reaction. So this kind of sums up what we just talked about. So in the next 2 slides, I just want to hit upon 2 topics. I want you to be exposed to this information. It might not necessarily come into any applied problems as we go forward, but it is important that you know this terminology. So I want to cover pseudo first order reactions. These are extremely common in natural systems. And so I want you to understand this term, the pseudo first order, what it is, and why we do things this way in natural systems. So let me explain. So you can imagine that in natural systems, a lot of things are second order. Two things coming together, reacting, forming a product. That is a second order reaction. So again, let's say it's A plus B going to P. This is our rate law for that, knowing that it's second order. First order with respect to A, second order with respect to B. However, second order reactions are really hard to follow in natural systems. And the reason for that is you have to monitor both A and B over time. That can be a lot for an experiment to be able to monitor both A and B over time. In the laboratory, maybe not so much, but out in the field, it's really hard to do. But in a lot of situations, you have to think about what's actually going on is maybe either A or B are fairly constant through time. So even though they're reacting, maybe one of them is close to being constant. An example of this is, say, what if B is at very high concentrations and in excess? So that means over time, even though it's reacting and it's part of this second order reaction, its concentration really isn't changing over time. So you're not seeing a curve come down with respect to B, but with A, let's say at a low concentration, it is changing. Well, if that's the case, then for B, you can say that it's constant and you can kind of wrap it up as part of the rate constant. If it's constant, it's a part of that overall constant. And now our very complicated rate law, where we had to measure two things changing at once, now becomes a pseudo first order. We know the process is second order, but we can model it as if it was first order. And that simplifies things a lot. So you will see this, some of you will see this later on. You'll see this term, pseudo first order, and that's what they mean by that, is modeling something other than a first order, most likely a second order, but in nature, as observed, it appears to behave like a first order. So an example of that, again, let's deal with our particles, and this is a adsorption-desorption reaction where, say, again, in the marsh, you have lead coming in from the influent, coming into the plant, and it's reacting with the many particles, and there's lots of particles. They're numerous in the marsh, but lead is only in trace amounts, very, very small amounts. Lead likes to absorb onto particles, especially particles that have mineral interfaces. You know, if you have oxygens with negative charges, that's a nice place for lead to adsorb and stick to particles. And so we look at this reaction, and this is the rate constant for this reaction going forward. We're going to say that the reverse rate is negligible, but nonetheless, this lead sticks to the particle. The lead concentration in solution is changing over time, but the particle concentration is not. Well, if that's the case, we can model the change in the lead concentration over time. We can model it as a first order, pseudo first order reaction, using this model. Last topic, Arrhenius equation. I just want to remind you that the rate constant is constant over time. However, it can be affected by temperature. The rate of reaction can be affected by temperature, and it can be affected by the value of the activation energy. This is pretty intuitive to you. You know that reactions are faster at higher temperatures, and that is the case. That is explained by this equation. Secondly, if you lower the activation energy, you will speed up the reaction. And so if you have some reactants to turn to products, they have to overcome, with respect to energy, some threshold. In order for them to react and collide, they have to hit each other at a certain amount of energy in order for them to create the products. We call this energy threshold the activation energy. The higher this activation energy, the slower the reaction will be. So again, the activation energy is the energy threshold that needs to be overcome for reactants to turn into products. And we have lower activation energy, something like this. That would be faster. We'd get a faster rate out of that if it was lower. And this is the principle behind, say, catalysts. What do catalysts do? Why do they speed up the reaction? They speed up the reaction because they lower the activation energy. Essentially, they give the reaction a new pathway to go from reactants to products that has a lower energy, activation energy. So that concludes chapter 2. This was a lot of information. I mean, we covered thermodynamics, equilibrium, and kinetics. This is something that takes 10 weeks or more in a general chemistry course, and we've covered it in 2 weeks.